Leah, here's what we're going to do today. First of all, let me point out to you, exam 1 has been delayed by 1 day. It was one class period anyway. It was scheduled for a week from today. It's going to be the following Monday from a week from today, February 19th. The Chapter 12 homework I'll hand out before the period's over today, and that'll be due next Wednesday. And we're going to spend 10 or 15 minutes to polish off Chapter 11 and then get well into Chapter 12, so you would actually be able to do about half the homework by the time we're done today. All right, we got this far talking about aromatics, benzene. We might have gotten a few more slides in this, but to just pick up where we left off. These are all ways of drawing benzene. Structural formula. Here's a line formula with the conjugated double bonds or a circle. Those are all acceptable drawings of the molecule benzene. Just some examples of benzene with things on it. Chlorobenzene, nitrobenzene, ethylbenzene. This molecule here, if you Googled that, it probably would say the name is toluene, and an alternate name is methylbenzene. But I would like you to know this as toluene. You might want a 3x5 card for that. A benzene with a methyl on it. You're eventually going to be introduced to all of these in Chapter 12, Chapter 15, Chapter 14, and others. There's going to be some other molecules where we got a benzene ring with a certain functional group on it, and I'm going to have you add that to your collection, but you don't need to do that right now. So there is phenol, aniline, benzoic acid. So the aromatic, the 6-membered aromatic ring is a pretty versatile ring. There's a lot of different molecules that are built on that foundation. So let me go back to this ortho, meta, and para and talk about it a little bit. Let's put our toluene over here from the next slide. Here's our toluene. Now, I'm going to draw 3 more molecules here. I'm going to put another methyl group on this benzene ring. So now we got that molecule. It has 2 methyl groups on it. Here's another one with just 2 methyl groups on it, but they are different. Yes, Zena?
Why is there a circle in the middle?
Because it's benzene.
Okay.
I could draw it just like that.
Okay. I just got confused for a second.
But the 3 double bonds in the circle or in the ring or a circle around the ring mean the same thing.
Okay.
There's just 2 different ways of drawing it. And then you can imagine one more example here. And actually, those are the only 3 examples. This molecule, by the way, where this one is called toluene, this is called toluene, that's its common name. This molecule is called xylene. These are all xylenes right here. Xylene. 3 different xylenes. Now, if you might say, well, you put one there, you put one there, you put one there. Couldn't you put one there and have another molecule? Can you see that if that methyl were here Can you see? I mean, I probably could draw these a little nicer, but can you see that this is identical to that? You know, I could rotate this boink and lay this right on top of that one. So there's nothing different about these two molecules. So what I want you to see is that these are the only three different molecules I could draw with a benzene ring with two methyls on it. Those are the only three unique molecules. I can't just rotate this one over and flip it on top of that one. Or I can't pick this up and set it over here. That methyl would be here, not there. Wouldn't be superimposable. It's different, right? Yes? This is different from that, which is also different from that. So those are the three xylenes. And this is a classical way of naming things. We consider this the ortho position. We consider this the meta position, and this the para position. Moving around from the top. You pick one, that's the reference, and so 1 over from the reference is ortho, 2 over from the number 1 methyl that's on there is meta, and 3 over, completely opposite that one, is para. And so this would be called orthoxylene. Or you might see it as just O-xylene. Not like O. Henry. This is O-xylene. Nothing Shakespearean about it, or whoever O. Henry was. This would be meta-xylene, or M-xylene, and this would be para-xylene, or P-xylene. Okay? So this is the ortho-meta-para nomenclature. It's a traditional, classic, old way of naming benzene molecules that have two substituents on them. Well, just to let you know, we could have, for example, we could have this. We could have a chloro group right there, and we would call it meta, because it's in the meta position, metachlorotoluene. All right, they don't have to be two methyls. When we have two things on there, we're going to name the thing, and then if it's in the ortho, meta, or para position, we could use the ortho, meta, or para. So this would be called metachlorotoluene. Okay, now your homework has you drawing. It says draw para something or other. So you have to know what, or it actually just have a P dash with a name after it. So you need to, oh, this is para. It's going to be opposite the one at the top. Now, this is the ortho, this is the meta, this is the para position, and I'm going to just give you a simple little way of trying to remember this. That's a boot. It's not a cis or a trans boot. It's just a boot. And so put the ST on there and you have stomp. Okay? STOMP. To kind of help you remember what order do these come in. Ortho is the first one, meta, and then para in the bottom. Stomp. You won't see this a lot. Don't think, but when you do see it, and you might see it you might read a technical article, and it says this was ortho bromo something or other. And you know, what is that? What are they talking about? I've never heard that. Well, you've heard about it. Or you just see an O prefix or an M prefix or a P prefix. You can assume that there's probably a benzene ring in this compound, and the thing they're talking about is in a particular position around the benzene ring. All right. I think we got this far. Did we? Phenyl? I think we did, but let me just redraw this a second. We got 5 carbons. It's a pentene, so there's 1 pentene there. I'm just reproducing this molecule right there. But on this 4th carbon, we have a benzene ring attached. There's a hydrogen here, a hydrogen here, 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 and here. We've replaced this hydrogen. It's now bonded to the carbon on the ring. And it's on the 4th carbon. There's carbon number 1, 2, 3, 4. So this is a substituent, just like you might see a methyl, like if that were a methyl or a methyl there. It's a substituent on there. We don't call it benzene now, we call it phenyl. And we say what carbon it's on, just like we would with the methyl or ethyl group. You can see the YL is almost always used, always give you an indicator. This is a substituent. This is the name of a substituent on the side of the chain. So when you see a benzene ring like that, we call it a phenyl. I won't mention a lot here. We'll get into this in chapter 20 when we talk about DNA and RNA. Heterocyclic aromatics. Benzene is not heterocyclic. It has all carbon. All the atoms in the ring are carbons. So it's not heterocyclic. But here are some ring structures with 1, 2, 3, 4 carbons, 2 nitrogens. That's a pyrimidine. Here's 2 rings that are fused together. These 2 carbons are common to that ring and to that ring. So those 2 rings are fused together because they actually share these 2 carbons. And you can see there's 4 nitrogens in it. That's a purine. So purines and pyrimidines are the nucleic acid, the structures that make up nucleic acids in RNA and DNA. And don't worry about them now. We'll worry about them in chapter 20. But do grasp, what do we mean by a heterocyclic aromatic? It is an aromatic molecule that has 2 different elements in the ring. Usually nitrogen, but it could be oxygen or sulfur. There's some other atom in there other than carbon. Usually carbon dominates, and there's something else there with the carbon, helping to form the ring. Okay, now, there are several reactions we could talk about in terms of aromatics, but this is the only one I'll kind of hold you responsible for, the halogenation of an aromatic. And benzene is the example here. Now, in this case, it's good. We got the structural formula. You can see you've got 6 carbons, 6 hydrogens. There is 1 hydrogen on each one of these. So just like with the alkanes, this reaction is a substitution reaction. It's not addition. We're not adding the halogen across a double bond in the benzene. We are substituting. So here is our aromatic ring. And if this is our chlorine, substitution. This chlorine is taking the place of the hydrogen, and the hydrogen is taking the place of the chlorine. So because it's substitution, you only get one chlorine on the ring, and you generate HCl. All right, even though the aromatics are in Chapter 11, Chapter 11 has double bonds, and you've learned that halogens add across a double bond. They don't do that with an aromatic molecule. They substitute. And the iron chloride here is a catalyst. So this is your catalyst. I'm sure there's other catalysts, but this is the common catalyst for halogenating an aromatic. So you could halogenate toluene or xylene in similar fashion. All right, so there it is written out as a chemical reaction. Benzene plus Cl2 forms chlorobenzene plus HCl. There are other reactions. At the end of the chapter, it shows the reaction with nitric acid to form nitrobenzenes, and I think there's one or two other reactions mentioned there, but this is one that you should keep in mind. All right, just a couple slides quickly to summarize the reactions in Chapter 11. So you have 4 addition reactions of alkenes. The symmetrical one, hydrogenation. Symmetrical, halogenation. Unsymmetrical, hydration and hydrohalogenation. Markovnikov's rule. Applies here and here because they're unsymmetrical reactants. And then if you wanted to summarize more or less all the reactions, so yeah, just keep in mind this halogenation and this halogenation proceed differently. Yeah, this says that Markovnikov's rule. Markovnikov's rule applies here and here to hydration and hydrohalogenation. Okay, any questions? Any questions about Chapter 11? All right, let's